Hello guys. Today we're going to be talking about number systems, which is actually a really crucial part in the ACSL curriculum. First of all, let's reflect back to what it actually means for a number to exist. We have here the number 13,145, a number that we may very well see in real life. Well, what does it actually mean? Numbers can actually be separated into digits, and each digit represents a different value. For example, the 1 here, which is on the 5th digit from the right to the left, represents the value 10 to the 4th, meaning that each increase in value within this digit would refer to an increase in the value of 10 to the 4th. Essentially, what this number translates to is the following expression: 1 times 1 times 10 to the 4th, 3 times 10 to the 3rd, 1 times 10 to the 2nd, 4 times 10 to the 1st, and 5 times 10 to the 0th, which is basically 1. That's a quick recap on what it means for our number system, which is base 10, or as we all call it, a decimal. Then let's do a very quick refresher on how to count from 0 to 10 in binary systems. First of all, we have 1, 2, 3, and we keep adding until 9. Then after we add 1, what do you think it's going to be? Well, you might say, oh, I know, it's going to be 10. Well, you're actually not wrong. Indeed, it is 10. However, why is it that when we move on to 10, we turn into a two-digit number instead of remaining still as one digit? That's because in base 10, there are only 10 symbols representing 10 values, meaning that there is no symbol representing the value 10 in base 10 number systems. And that's why when we reach to the value 10, we actually have to carry over the value of 10 to this digit, meaning that every digit on the second digit represents 10 in the first digit, as illustrated here. Therefore, for example, if we have the number 99 and we try to add 1 to it, what we have is that we see that 1 plus 9 equals to 10, meaning that, and since there's no value representing the value 10, then we carry over the 1 to the next digit, to which again there's no value, no symbol representing the value 10, which we then carry over another 1, which turns out to be 100. After giving a quick recap as to base 10, or our decimal number system, let's move on to talk about binary, the buzzword, or base 2. As we can see here, we have a binary number 10100. And much like the decimal base 10 number system, each of these digits in this binary number has a different value. From the right to the left, it starts off with being with each digit holding a value of 1, value of 2, 4, 8, 16, and so on. And so this number 10100 is actually 1 times 2 to the 4th, which is here, 0 times 2 to the 3rd, 1 times 2 to the 2nd, 0 times 2 to the 1st, and 0 times 2 to the 0th. I would like to put a little emphasis on how you pronounce this number. It's not 10,100, it's 10100. 10,100 is how you would pronounce it if it were a number in the base 10 system. Now let's move on to the next graph. In this graph, we see that again we're trying to count from 0 to 10. In this column, we have already finished this column in the previous slide by counting from 0 to 10 in base 10. Next, let's try to count from 0 to 10 in base 2. Of course, the first value is always 0. Then after we add 1, it's still 1. However, after we add 1 again, since there are only 2 symbols within the base 2 number system, 0 and 1, therefore we don't actually have a symbol that represents the value 2. And so in that case, since now we have the value 2 on the rightmost digit, we carry over that value into the digit on the left, which would turn out to be 10. As you can see here, the 10 refers to 2 to the 1st times 1 plus 2 to the 0 times 0, which equals to 2. this is equal to the base 10 representation of the number 2. Then after 10, we try to add 1 again, which would turn into 1, 1. Sorry, I apologize, not 10, 1, 0. After the 1, 0, we add another 1, which turns into 1, 1. After that, if we want to add another 1, what would happen is that 1, 1 plus 1 would actually turn into, first of all, this column of digits are being added, and the value here would be a 2. However, since in base 2, there is no symbol that represents the value 2, we would have to carry over 1, meaning that the second column would have the value 2 again. And then we would have to carry over again, meaning that the final product would be 1, 0, 0. 1, 0, 0 here refers to the value of 4 in base 10. And like this, we keep on adding 1 until finally we get 1, 0, 1, 0, which would correlate to the value 10 in base 10. And so down here, we added a quick little summary. The value 10, or the number 10 we use every day in our lives, actually equals to the value to the number 1010 in binary. On the contrary, the value 10 in decimal does not equal to the value of 10 in binary, because 10 in binary actually correlates to the value of 2 in base 10. Now that we've given you guys a quick introduction on binaries and decimals, let's move on to some questions and calculations. First of all, let's do a quick calculation, a quick addition in decimal. This is basically what you would expect in your typical math class. In here, we first perform 4 plus 6, which would provide us with 10. We all know that we have to carry over the 1. So now in this column, we have 1, 2, and 3, which adds up to be 6. Then, since there's no carryover, we just drop the 1 right down, and this summation would become 160. In binary, this is also the same case. What the binary does is, first of all, it looks at the rightmost column. It sees that 1 plus 1 would equal to the value of 2. However, in the binary number system, there is no symbol that represents the value 2. There's only a symbol that represents the values 0 and 1. And so therefore, we've dropped down the value of 0 and we carry over a 1. Now, in this column, again, we're faced with the fact that the sum of all of these values sum up to be the value of 2. So again, we drop a 0 and then carry over another 1. In this column, again, the sum is 2, so we drop a 0 and carry over a 1. Again, in this column, 0, carry over 1. And finally, in this column, the sum is now 1. And so we don't have to carry over anything, and we just have to drop the 1 here. And for this final column, we just have to drop the 1. And so eventually, the sum of 101011 and 101 turns to 110000. This is, as you may have noticed, this sort of addition is very similar to the decimal addition. And just to confirm our results, let's convert all of these numbers into decimals and see if the addition results match up. 101011, when converted into decimal, actually turns into 43. 101, when converted into decimal, turns into 5. And our answer, 110011, when converted into decimal, turns into 48. And so after we add up 43 and 5, we find that the answer is indeed 48, which means our calculations in this binary system was correct. Now let's quickly perform another the subtraction operation in binary. First of all, we have 1, like in base 10, we start off with the rightmost digits. 1 minus 1 equals to 0, so we drop a 0 down. 1 minus 0 equals to 0, we drop the 0 down. 0 minus 1 is actually, 0 is, we actually have to carry over a 1 from the left digit, which would turn this digit into the value 2. This is because each value from the digit on the left equals to 2 of the value of the digit on the right. And so here we have 2 minus 1, which is 1. And since this digit has already been carried over, this digit is a 0, and we just drop the 0. This one also 0, this one also 1. And so we find that the subtraction of 1 0 1 0 1 1 and 0 1 and 1 0 1 equals to 1 0 0 1 0 0. This operation would also work in base 10, and I suggest you guys to also, like before here, to try and do it yourselves to double check the work. After talking a bit about binary addition and subtraction as well as its relations to the decimal number system, we also want to introduce two more base systems. These are base 8 and base 16. For base 8 specifically, it is called octal. Here is an octal number, 46375. And very similar to binary as well as decimal, each of these digits represents different values. The rightmost digit represents 8 to the 0th power, and then 8 to the 1st, 8 to the 2nd, and so on. And so 46375, if you were to convert it into a base 10 number, would become the value 4 times 8 to the 4th, 6 times 8 to the 3rd, 3 times 8 to the 2nd, 7 times 8 to the 1st, and 5 times 8 to the 0th. This is base 8. Then, moving on to base 16, which is referred to as hexadecimal, this is basically saying that this number system has 16 symbols representing 16 different values. However, in our current decimal system, we only have 10 symbols representing different values. And so in a hexadecimal-based number system, we would actually have to add 6 more new symbols to represent the values of 10, 11, 12, 13, 14, and 15. And so the computer or base number system people thought of using the symbols A, B, C, D, E, and F. So think of these letters right now as the symbols representing these different number values. And so if we look at this expression, which is actually a number in the hexadecimal number system, we see that, again, each different digit represents a different value. From right to left, 16 to the 0th power, 16 to the 1st, 16 to the 2nd, 16 to the 3rd, and so on. If we were to convert this hexadecimal number into a decimal expression, we would perform the following, which is 3 times 16 to the 4th, 10, which is also A, times 16 to the 3rd, 4 times 16 to the 2nd, F, which is 15 times 16 to the 1st, and B, which is 11 times 16 to the 0th. This would be a conversion between the hexadecimal and the decimal number system.